konnichiwa. Okay. Konnichiwa, Mr. Goto and everyone. We are group 11.
Group 10,
right? Okay, we are group 10, sorry. Today, we are going to analyze the film series, Despicable Me. In short, it's the story of a man who wanted to become the world #1 villain and begins by adopting 3 orphan girls. Though the story is humorous and touching, there are a lot of physical mistakes in it. Without further ado, let's start our presentation. First, let me show you the video.没关系，有画面就好了。Okay, though it's impressive, but is it realistic from the physics point of view? In here, I want to ask 2 questions. First, can the minion push a 6-meter tall rock? And second, can the T-Rex walk on a boulder that's going downhill? So let's discuss the first question. As the left picture we can see, the rock is staying nearly horizontal in the ground. So here's my assumption. First, the rock shape will be perfect sphere. And second, it will be 6 meters tall for its diameter. And third, his density will be 2.5 grams per centimeter cube. And okay. So let's calculate it. The value of it will be 4 divided by 3 times pi times r cubed, and will be 113 meter cube. And the density of it will be 2.5 grams divided by centimeter cube. So we can calculate the mass of it will be 282,000 kilograms. And the fraction of the ground and the rock will equals to the maximum static friction coefficient times normal force, and will be 1.6 million Newton. But we can see the maximum push force of the minion only be about 200 Newton, and is the torque to move the rock will be about 5 million Newton. So we can get the calculation that even on a slope, the minion's force is too small to push the boulder. So it's physically impossible. And now we are going to talk about our next question. Can the T-Rex walk on a rolling boulder? Because I'm going to discuss the very junction that the T-Rex jump on the rock. So I will get the assumption that the boulder is not rotated, and it is fixed on the 30-degree incline slope. Also, the maximum static friction between the T-Rex and the rock will be 0.5. So let's calculate it. We can get the component's force that's caused by the weight of the T-Rex will be 34,000 Newton, and the fraction between T-Rex and the rock will only be 29,000 Newton. So we can get the calculation that the component force that's caused by the T-Rex wedge will be bigger than maximum static friction of the T-Rex and the rock. So the T-Rex will fall down immediately. Even the rock is rolling like the video shows. It's also impossible for the T-Rex to stay on it because he has to get the opposite speed. That's the rock rolling down. So the scan in the video is impossible.
Okay, so I didn't understand this part. Why is it possible? I didn't understand.
Because the T-Rex stand on the rock and he gets the wedge, and the T-Rex is he is 7,000 kilograms.
Right.
And he will get the component force that will make it fall down. And the maximum friction of the T-Rex and the rock is smaller than the component force.
I don't understand why T-Rex cannot stand on the ball. Why he falls? Is this related to the rock? So if T-Rex stands on a slope, you're saying he's gonna fall?
In the scan, the T-Rex is jump onto the rock.
Okay, so T-Rex jump on the rock and then?
And then at that moment, we can get about two forces. One is friction force. One's caused by the wedge of T-Rex itself.
Right.
And we can discuss the component force that is about T-Rex wedge and the friction, maximum static friction between the T-Rex and the rock. If the component force that's caused by the T-Rex is bigger than the maximum static friction, it will get, I don't know what to
So this has
slide.
nothing to do with the rock, right? So T-Rex jump on a slope, and then you are saying T-Rex is going to fall?
Yeah.
I don't think so. Well, I don't understand why he falls. Because his legs can...
In the conclusion, I say that the rock falls down from the top of the mountain, and it got the inertia. The inertia is we cannot get the speed that the rock falls down from the mountain. So I just discussed that the rock is not rotated in the moment. But in the conclusion, I have to say that because the T-Rex need to overcome the inertia and also the maximum friction.
That's not what you explained in your previous slide, right? So the rock is round, right?
Sure.
So you can jump on a flat place, not on a slope. Then there's no force, so there's no component force, right? Then he's not going to fall.
No, but in my assumption that I say that the rock is falling down from the inclined slope that is about 30 degrees.
Yeah, throw an arrow, yeah, there's flat, right? 0 degree, right? Okay.
Sure.
What do you think? Do you understand what you're saying? Yeah, but I didn't understand. Okay. So I think your point is interesting, but I just couldn't understand. So can you explain more detail in your report, please?
Sure.
Yeah. Okay. Okay. Next person. Thank you, Emerson. Next.
Hello, I'm Lawrence.
Lawrence.
Yeah, and the clip I'm going to analyze is the shrink rate. So let's see a clip first.
Okay. Can you explain the program while we're watching?
Okay. So there's a normal elephant,
Yeah.
and this is the shrink rate.
Okay. So make it small.
Yeah,
Shrink rate something. So that's what I wanted to explain. To explain the scene, please.
so the shrink rate will shrink the elephant to a really small size.
Okay.
Okay, so this is a clip. And my question is a shrink rate theoretically possible?
Okay.
And first, we have to do some assumption. And the mass of an elephant is about 5,000 kilograms, and the volume of it is 5 cubic meters. And I made the linear downscaling factor is 100, which means if the elephant is 4 meters tall, and after shrinking, it will become 4 centimeters tall. So using this factor, we can easily calculate the reduced size. So after calculating, the elephant's size will become 5 times 10 to the minus 6 cubic meters. And the first aspect we can analyze this is the conservation of mass. Because the mass won't be shrink, it will remain. So the only thing changed is the volume of the elephant. Then we can calculate the density after the elephant is shrinked. So we can use the mass of the elephant to divide the volume of the elephant. And we can get the density after shrinking is 10 to the 9th kilogram per cubic meters. And that is too big. It's higher than the highest density element on the Earth. And in the universe, the same density thing we can find is the white dwarf. So that's impossible for this kind of density to appear on an elephant. So it's impossible to shrink the elephant by the aspect of the conservation of mass. The real consequences is the shrink rate. When the shrink rate hit the elephant will instantly explode.
Why explode?
Because the density is too big and the pressure that the atom and the molecules cannot afford the pressure from the
If the pressure cannot be supported, it's going to explode.
Because the molecule and the atoms is the same as the elephant before shrink. So after the shrink, the density will be too big and the atoms will be too crowded.
So it's going to explode?
It turn into dust, and it can remain.
In the report, please explain why it's going to explode, because I don't think it's going to.
Okay. So the next aspect is conservation of the energy. And we can use the equation E equals Q plus W. And if we need to calculate the work that shrinking an elephant is required, we can use this equation. And the K we use in this equation is called bulk modulus. And it's a measure of substance's resistance to uniform compression. And because there are about 80% of water in the elephant, so we take the bulk modulus of water. It's 2 times 10 to the 9th pa. And using this factor, we can calculate the work we need to shrink the elephant into the size that we required is 1.5 times 10 to 11th joule. And it's too big for an elephant to afford this kind of energy. And even the shrinking race machines can't afford this energy too. So theoretically, the elephant shrinking is impossible.
Bulk modulus doesn't work at an atomic level, I think. But anyway, yeah, go on.
Okay. This is my part.
Okay. Okay. You have some problems. Well, Lawrence, okay, I think you picked up the program. It's interesting. So that's good. But I think your analysis has a little problem. So here, okay, second part. Bulk modulus is, first of all, it's bulk modulus, U, cannot be used for atomic level. This is only a little bit, like when you push someone, and then, when I push, my bone is broken, yes, then you can use bulk modulus. But you cannot crush the atom, that's a different force. You know, it's not this bulk modulus.
Oh.
Right, so can you please calculate? Okay, let me think. Can you, what's the real problem? Okay, how much smaller can you make the elephant?
How much smaller?
So why you cannot make the elephant smaller? What's the problem? Okay.
Because
what forces? Okay, there are a lot of forces. Electromagnetic forces. Well, this is a class to learn electromagnetic force. And then, well, the atomic forces we don't do it, but the nuclear forces, right? So which one is a problem? Weak force, strong force, electromagnetic force. Which one is going to be a problem, and how big it is? Okay, can you calculate that? That's more real physics. And then previous one, I don't think it's going to explode. And you cannot just guess things. Then you're the same as the animation. So if you think it's if you think it's going to explode, please explain. If you don't think it's going to explode, please modify your statement in the report. Okay. Good. Lawrence. Yeah.
Thank you.
Who's next?
Silent.
Simon. Interesting name.
Because this is a wish I want to have, but I never fulfill. Okay.
Don't be silent in your.
Okay. Hello everyone. My part is want to introduce the main concept in the first episode, Still the Moon. This is also about the shrink rate, but what I emphasize on may be a little difference of the previous members introduced. So let's watch a clip first. Girl use shrink rate to shrink down the moon. Sorry, I don't know why it's like. and the moon becomes smaller, smaller, and smaller, and then finally, okay.
Is that the shrink rate?
Yes, what he holds is the shrink rate, and then finally become a size of hand.
Okay.
And the later clip is that they take the moon back to the Earth, and well, the moon was taken away by another villain. As you can see, the moon getting bigger and the weights become, it become heavier, and even make the spaceship, even make the flagship tilt. Oh, well, so my question is it possible for good taking the shrunk moon back to the Earth successfully? Okay. First is the basic statistics. Okay, the radius of the moon is 1,735 kilograms, and this is my hand. Okay. Okay. Well, I measure my hand. The diameter is like 12 centimeters. But Gru is a male adult, so I exaggeratedly assume that the radius of the moon after shrunk is 10 centimeters. Okay, and I think there are two ways how the shrink rate function. And possibility one is only the volume changed, but the mass didn't change. And the possibility two is that density didn't change, and so volume and the volume and the mass change. Okay, for the possibility ones, what I'm concerned about is the gravitational force. So I assume that because Gru is a male adult, so I assume that the mass of Gru is 80 kilograms. And the distance between Gru and the moon is 2 meters because he wants to approach the moon to get it. So I use the gravitational force formula. Force equals the universal gravitational constant times the 2 mass and the divided r squared. And we get a very, very huge force, 9.82 times 10 to the 13th newtons. So I think Gru can slowly approach the moon and grab it. I think he will crash upon the moon and make him harm. Yeah. For the possibility two is the density didn't change and the volume and mass change. The density of the moon is 3,340 kilogram per cubic meters, and the speed of light is 3 times 10 to the 8 meters per second. I use the energy equivalence relation. Energy equals mass times speed of light squared. And the change volume, I forgot to mention that I assume the moon is a homogeneous sphere. Okay, and then so the change volume is 4/3 pi times the cubic radius, and then we get the change volume. Then the change volume times the density, and we get a changed mass. So the energy release, we plug the number back into the formula, and we get a very strong energy, 6.59 times 10 to the 39. And for research, I found that the monthly average electricity consumption for a family in Taiwan last year is 1.25 times 10 to the 9 joules. And I use this to divide the statistic I mentioned. So the people can use the energy for 5.27 times 10 to the 30th months. So you can know it's a very huge energy we have. So I think Guru may be burned to ash in the energy wave, or maybe fortunately he survived the disaster. I think he will be sent away in the flow in the space. So in conclusion, I think Guru can take the moon back to the Earth safe and sound. So this is my conclusion.
Okay, excellent. So, very nice. Where was the moon?
Where was the moon?
Yes.
Moon. You mean in the animation or?
Yes, in animation. Right? So you're saying take him back to the Earth, but where was it?
Oh. No, they are in Earth now. Yeah, and the moon become bigger in the flagship.
So is it in the moon's orbit around the Earth? The moon was in the orbit of the Earth?
No. The moon was taken back to the Earth.
Yeah, so from where?
Huh?
From where?
From where? From the orbit. The moon was shrunk, and he take the moon to the Earth, back to the Earth.
Okay.
And the other didn't get it.
Okay. So suppose you clear these programs, and then in your report, can you think about how to get the moon back to the Earth? Because moon has a momentum, right? Moon is moving, right?
Yes.
So it's very difficult to get back to the Earth. So can you come up with the idea how to do it?
Okay.
Anyway.
Okay. Thank you.
Maybe. Rina. Okay.
Good morning, everyone, and I'm Rina from Medical Science. And today I wanna share this clips. It's about the other villain get the moon, and after that, the three doctors of Guru still on the other aircraft, and Guru try to help them, try to save them from the aircraft. So let's see the video first. So, they want to jump, Mr. Guru want they to jump from this aircraft to the other aircraft. And he will catch them by his hands. So let's see. So, okay, after watching these clips, my question is, will Mr. Guru's hands will remain intact after he catching his two doctors with his bare hands? So let's analyze these scenes. And before calculation, we have to figure out those numbers. And first, I use officially height of Guru, and he is a male adult, so his height is about 2 meters. And according his height, I estimate the horizontal distance between two spacecraft and the vertical height distance. And I get the number like 13 meters and 6 meters here. And his two doctors combined mass is 55 kilogram here. So since we get these numbers, and we can start calculation right now. And I assume the height is 13 meters here, and the gravitational acceleration is 9.8 per meter per second square. And I use the free falling equation here, and h equal half g t squared. So I can get a t is 1.1 seconds. And then we use the distance here and divide by the falling time. And so we can get the velocity of horizontal is about 11.7 meters per second here. And then, since we get the horizontal, we want to know the vertical, so we can calculate the combined velocity. So we use the falling time with, we take the falling time and times with gravitational acceleration. So we get the velocity of vertical is about 10.9 meters per second. And then we combine these two components and we can get the 16 meters per second here.
That's very fast.
Oh.
Go ahead.
And in this part, we will use momentum and the impulse concept to figure out the impact force here. So as we mentioned before, the two doctors' combined mass is 55 kilograms here. And the velocity is 16 meters per second. And we will use the momentum equation is P equal mass times velocity. And put this number in this equation, we can get the numbers about 880 kilograms times meter per second. And then the impulse is the momentum change. And the momentum change equal force times time change. So we can get the force here is momentum change divided by time change. And momentum change we can replace with mass times with velocity change. And since the velocity of final, they catch, Mr. Group catch them, and so they will stop. So the velocity final is 0. And the velocity initial we assume is 16 meters, just calculate before. So, and we assume the stopping time is 0.1 seconds. So we can get the number of force is about 8,800 Newton here. So back to the cartoon, and we can see the Mr. Drew's hands remain intact here, right? But in the real life, is it possible or something else? And in the real life, our body joints, they can stand with different force. And about our wrist is around 1,000 to 1,500 Newton. And for our shoulder, it's more strong, so it can stand with 4,000 to 6,000 Newton. But based on our calculation, the 8,800 Newton is far from the limitation. So, is it possible? I think, in my opinion, Mr. Group's both arms will hurt and maybe dislocated, but definitely won't remain intact here. So that's my part.
Okay, very good, Rina. How do you get the 13 meter and 6 meter? Before that too much.
I use the because he is 2 and I start calculate and I use this picture to estimate. I think maybe.
How tall is the
2 meters. And I use this, oops. I use this picture to assume. But during my calculation, I found that he is standing here. Yes, I found it in the morning.
Okay, so I think the program is here, right?
Yes.
30 meters and 6 meters. First of all,
Yes.
Jump 30 meters in how many seconds?
6
seconds.
Yes.
Almost impossible.
Yes, this is the other question I want to investigate, but because the time limitation, so I choose the other question.
Okay, so in your report, can you calculate how much closer he needs to be to make this successful?
Okay.
If he is closer, it's okay, right?
Yes.
So, yeah, can you think about that?
Okay.
Okay, but very good report, Rina. Thank you.
Thank you.
Okay, very good. Your
Here. Okay. Sorry. Maybe I can. No. Okay. Hello, everyone. My name is Angus, and let's see this clip. Okay, Guru used freeze gun, and Lucy used a firestorm, and they cancel each other out. So this freeze gun is very amazing, and Christmas is around the corner, so I want to list freeze gun as a gift. But is this gun really? Can this gun really exist in real life? That is my question. Is this gun real exist? But we cannot image the freeze gun because we haven't seen that before. So we can focus on the firestorm because that has been used in World War II and has been used in a film ballerina. And we know when in this scene, the firestormer and the freeze gun cancel each other out. So the net change in heat is 0. In the other words, the heat generated by flamethrower is equals to the heat absorbed by the freeze gun. So let's calculate the heat generated by flamethrower first. The heat equals to the heat value times volume in above. And if we use diesel, the heat is 35.15 million joules per liter.
If you use what?
If we use diesel.
What's diesel?
Diesel. DIES, a kind of oil.
Diesel.
Oh, diesel, sorry. Sorry about that. Diesel. If we use diesel. So the heat value is that. And according to the World War II data, the flow rate is 1.5 gallons per second. And according to this video, the time is 1. So the total volume is 1.8925 liter. In the end, we can calculate the heat generated by flamethrower is 36.52 million joules. Again, the heat generated by flamethrower is equal to the heat absorbed by the freeze gun. So the heat absorbed by the freeze gun, also the 66 0.52 million joules. According to the second laws of thermodynamics, we can use the coefficient of performance to calculate how freeze gun transmit the heat. Assume a COP is 7. That's very powerful. So the total heat observed by the freeze gun is 76.02 million joules. And finally, we can calculate how hot the gun is. Assume this gun is made of aluminum and weighs 5 kilograms. Use this formula, Q equal mass times C times change. So we can get the, this is a temperature change. So we can calculate the temperature change is about to 16,676 degrees Celsius. That's 3 times hotter than the surface of the sun. That's very hot. So in a reality world, this gun, when the group press the trigger, the gun will melt instantly and group will completely hurt and burned. So that is all my presentation. Thanks, everyone.
Sorry. The gun, the heat gun is the lady, was held by lady, right?
Yeah, this
Glue is on the right, right?
glue is on the right. Yeah, and
The lady's gun will melt.
a lady also got melt. No, because
Why glue has a freeze gun and then it's going to be melt?
melts because we know this heat generated by flamethrower, and this freeze gun, the function of freeze is move the heat from here to here, like air condition or freezing.
Is that explained in the video?
Yeah, I explain the function that freeze gun.
Sorry, is that explained in a video? Is that something you thought that's going to be the way it works?
Maybe it's my guess.
Okay, fine.
Okay, so I guess the function that, because the freeze gun is not exists in our world, so I guess the function in this video. Yeah.
Okay, so the first of all, you don't need to cancel the heat, I think.
Oh.
This is just a volume, right? See, you look at the heat, it's going somewhere. You don't need to cancel, you just deflect it, that's okay, right?
Oh.
So this is like a wind battle.
Wind.
Yeah, you don't need to cancel the heat. If you have a strong gun, have strong wind, or volume to push, then heat is going to go back to the lady, right?
Oh, but in the movie, it's group shoot first, and lady should stay in follow. So I want to use this heat to calculate.
So that's the first thing. And the second thing is, there is freeze gun in this world. So in your report, can you use actual freeze gun
Oh.
and then make it even?
Oh, use freeze gun.
Use that this kind of thing that to kill bugs,
Yeah.
cockroaches, and you have freeze gun and then cockroach is going to frozen to death.
Oh.
Yeah, you just try this kind of thing and then see if it works.
Okay. Okay.
Very interesting topic.
Thank you.
Thank you, Anders.
Okay.
Okay. And good morning, everyone. First, we can take a look at this movie excerpt. As you can see, the strongman in the video is called El Macho. That's the way. And he stopped the truck, the armored truck, by ramming it with his body. 我再播一次吗 ？OK。
So what's the problem? Okay.
Okay. This is extremely unrealistic in reality. So my question about this script is, how heavy will the person have, the El Macho have, to be stop a truck instantly? And let's see what actually happened when a person hit by a truck in real life.
This is not real life.
This video is a little bit ridiculous, yeah. But we can see that after being hit by a truck, the man was thrown backward and obviously suffered injury. Meanwhile, the truck slid forward some distance before coming a complete stop. So from this video, we can see that in the real world, a human body is hardly enough to stop a truck. And next, let's analyze and calculate the physical quantities. First, at the moment when the vehicle is parallel to the building, we assume that the height of one floor is the same as that most modern building. It's 3 meters high. And we can see the truck's height, the height of the armored truck is similar to that of one floor. So it's also 3 meters high. And these sizes are similar to this type of armored truck used in Taiwan.
Okay.
And this type of truck, after the modifications, it weighed around 3.5 tons and about 3,500 kilograms. This truck's weight. And this truck, its maximum payload is around 2,000 kilograms. And we can imagine as 2 billion new Taiwan dollars in cash, the weight. Okay. So, its total weight of 5,500 kilograms. Next, by comparing the height of one floor and the height of the hole in the wall, we can estimate that the man, El Macho, the man's height is about 1.9 meters. And also, I calculate his foot length and width, and we can get his foot length is 19 centimeters and his foot width is 8 centimeters, respectively. And since the shape of a foot is irregular, so I use the trapezoid as an approximation to estimate the area of the sole, which comes out to about 0.012 square meters. And next, using the height of one floor as a reference again, we can estimate that the person is about 5.19 meters away from the intersection. And in the video, it took the armored truck about 0.88 seconds to reach the person from the intersection. So we can get his speed is 5.9 meters per second. And it's about 21 kilometers. I'm sorry, there is kilometer per hour, yes. I'm sorry. And we can find the vehicle stops almost instantly after the impact. So now we have the armor truck's mass is 5,500 kilograms, and his speed is 5.9 meters per second. And we also calculate the area of the soil is 0.012 square meter. Also, different shoe sole material has different coefficients of friction. And according to a research, according to research, a shoe sole needs a friction coefficient about 0.6 to 0.7 that can prevent slipping on the dry ground. So we assume that the air mattress shoe sole friction coefficient is 0.7. Next, finally, we can calculate his weight, the main weight. Assume it took 0.1 second for a vehicle to come to a complete stop after the impact. So we can get his acceleration is 59 meter per and he need a friction about 324 and 500 newtons. So we can get his weight require a normal force of 464,000 newton, which is equal to about 47,000 kilograms. So now we know this person need to weigh 47,000 kilograms to stop the car instantly. And I also calculate the pressure on his feet. It will be 190.5 atm. That is my report. Thank you.
Can you go back? What's the collision time adjustment? So you're assuming it stopped in 0.1 second?
Because it's almost stop instantly, so we assume that it stopped in 0.1 second. Just stop in a very short time.
Okay. Yeah, good, Jeffrey. In the report, can you think about a way to make this work? You can increase the person, or you can decrease the collision time. Can you make it happen? Okay. Thank you very much.
Maybe we can.
Thank you very much.
Okay. Maybe we can take a shoes. Yes. Okay. Yes.
Hello everyone, my name is Mimi, and that's my video. Let's look at. And as we can see, they shoot out the building and fall straightly and float on the floor. So my question is, why is it physically impossible for them to float? And as my analysis, the initial trajectory diagram is like this. They shoot out the building horizontally, and they immediately fall down and finally float on the floor, not crash it. So this is not physical impossibly. The correct trajectory map is as they as they shoot out the building, and they have a parabolic path to crash the floor. And because as they shoot out the building, the force they only have is the downward gravity. And in the video, they don't have a downward jet engine to give them the upward force. So my calculation is, as the assumption is initial forward velocity they shoot out the building is 10 meters per second, and they shoot out a building and float on the ground is 5.01 seconds. And we assume the mass of flying car is 20,000 kilograms. And the time of hitting the floor is 10 milliseconds. And here we don't consider the air resistance because the mass of flying car is too heavy. And according to the formula, the velocity of the flying car hitting the floor is 49.098 meters per second. Is approximately 180 kilometers per hour. That's extremely high velocity. And in this velocity, the force of the flying car hitting the floor will be 58 million Newton. So they will die immediately. Yes. So my conclusion is this small flying car should have a parabolic trajectory and be equipped with a downward jetting engine to avoid crash into the ground. This is my.
So as you propose, please try to equip the downward jetting engine and then see how it works. Please put the engine downwards and then calculate if it works or not.
In the report?
Yes.
Okay.
Thank you very much. Okay, good meeting. The last thing.
Yeah. Okay. Hi, I'm Yvonne. Today I want to talk about the topic is free fall and impact force. So let's think those things. That's why it's Girl and Lucy on the rocket and they fell down and hit the ocean. And okay, so my main question is why is it physically impossible for them to survive? Because they fell down from very high rocket. So to know this question, we need to know how fast did they hit the water first. And I assume that the height of the rocket is, because it is higher than the volcano, so I assume that it is 1,500 meters. And the gravity is 9.8, the landing time is really short, so I assume it's 0.02 seconds. And the body mass of Girl, I assume is 65 kilograms. So first I calculate the velocity that hit the water. So I use the kinetic equation, velocity equal to square root 2gh. And so the calculate is square root 2 times 9.8 times 1,500. So it equal to 617 kilometers per hour. And this is really fast, but because we still need to consider two other factors like air resistance and the falling down position. So I assume that a girl is in a belly down style like this. So because the air resistance will cause one force called drag force. When the drag force equals to the gravity, the person who falling down will stop accelerating. And that moment, the velocity called terminal velocity. And the terminal velocity depends on the body position, the person falling down. And we use the average estimate I searched from Wikipedia. The one person falling down in panic is about 195 kilometers per hour. And it is much slower than 600 kilometers per hour, but it is still lethal. Why it is still lethal is because there is still a very huge impact force. So we use the impact force formula F equal to m delta V divided by delta T. The delta T is impact time, is 0.02 seconds. And the delta V is 195 kilometers per hour, and it equal to 54 meters per second. So the calculation is 65 times 54 divided by 0.02, and it equal to 175 Newton and about 180,000 kilograms of force. And this is really huge force. So when Lucy and Gru hit the water, it's not just normally hit the water, it's like hit a solid concrete. So they definitely become a burger patty. So in that case, I think if Gru and Lucy want to survive, they can choose other way to hit the water. The first one is, this is a water diver. And she used, and we can see her position, she used her hand to hit the water, so it can decrease the area to touch the water, and it can largely decrease the impact force. But in real, this player is only 10 meters high. But in Gru and Lucy's condition, there is 1,500 meters. So I think that is not work as well. So I think the only way Gru want to save is he can bring her parachute with him, because parachute can extremely decrease the velocity he falling down. So thank you, that's my part.
Okay, going very good. In your report, can you calculate these two cases? So if you fall onto the water, how much less forces, less impact on them? And how big your parachute needs to be?
Oh,
Okay,
thank
good.
you.
So you have quiz? Go ahead.
Physics work should I introduce?
Okay.
Okay, the word I want to introduce is Doppler effect.
Okay.
When there is relative motion between the wave source and the observer, and the frequency change. So LS is a formula, and we use plus when when them toward each other, and we use minus when they get away from each other. And we have two examples. Example one is when ambulance come toward you, and you will hear the peaks up because the frequency is getting higher. And when you sound when the ambulance leave you away, you will hear the down pitch because the frequency is down. And the other is in our astronomy, the red shift is star moves away from us, and the blue shift is star toward us. Okay, so this is the Doppler effect. And then we move on to the Kahoot.
Okay, just one comment. So the expansion of the universe is not causing the Doppler shift.
Oh, isn't that?
Please report me what's the difference between this and the Doppler shift.
Okay, how? Okay.
Then we have a quick. I'll be back in 30 seconds.
What's that? 你可以让昨天的目标再玩一次呢？还是？那你把参与者删掉，你把参与者删掉了。这个 report 可能要先弄掉。啊 ？report 已经断掉了。这个要先关掉。没有，不知道。
有人已经进来了，算了，这些人就不管。有人已经进来。
好。
能低调吗？不行。不能 P 掉，那就这样吧。
我们自己可能自己不要全打，自己可能不要全打。
You ready?
Yeah.
Okay, you guys cannot join. If you're in group 10,
Yeah.
you should join.
Okay.
So Mimi, you cannot join. Yeah.
This is previous because we practiced yesterday.
Okay.
No.
So please, if you're in a group, please don't join. Okay, because you guys created the question.
Yeah. Okay. And maybe we start or okay.
I join.
Okay. Okay. 你来操作了。Okay, let's start. Okay, the first question, what's the function of coefficient performance? Below is correct. Okay. Everyone are so smart. Okay, next one. This is yesterday. Sorry, that's yesterday point. I don't know why. Okay, the next question is the formula energy equivalence relation. Okay.
This is fine, but then you need momentum in reality. In general, you need to add a momentum.
Oh, momentum.
Yeah.
Okay.
This is correct if momentum is there, but then if you have momentum, you need to add the momentum.
Ah, okay. So this is a point we practiced yesterday. Sorry. What is the value of bulk modulus we use for calculate? But that is lies a little wrong in this presentation. But okay, the number is 2.10 to 9 power. Okay, next one. Okay, which of the following statement is true for the terminal velocity? Terminal velocity when something falls from the very high. Please consider the resistance of the air. And which of the following points would not affect the normal force? That guy need to stop the truck. Okay, the area of the shoes. That?
Area doesn't influence about the friction.
Oh, okay.
Yes, we go ahead first.
The groove how can groove reduce the impact force when catching the girls? Catch them faster, or use only one hand, or
Actually, jump backward is also fine.
oh, no wonder there are four.
Fine, go ahead, go ahead.
What is the main downward force on the car fall from the tall building? Downward force. Okay. Under assumptions we made, which of the following could realistically help medium push the boulder, medium push the rock? Okay, the final question. Oh, what's that?
The last one.
Which of following opinion is related to the Doppler effect? But we have to recorrect on our report. Okay, thank you everyone. And
Who's FEI?
this is the person yesterday.
Oh,
The first one is the yesterday person. Yeah.
okay, so FEI, please get the credit. Very good job.
Okay. Thank
Okay,
you.
So, can you put the Google Meet screen? You got joined, right?
Oh, okay.
Because I want to share a screen.
Screen here.
Oh, but first of all, thank you very much for
Okay.
for the event. Yeah, I enjoy your presentation. It was very good. So please also make sure to submit the report as well. Okay, there's not much time to report. I need to use that. Okay, so today, what are you doing? I need your screen, right? So, Faraday's law. That I want to make sure we look at the transformer today. I mean, this is okay. Good. So, do you remember the Faraday's law? Do you remember? We did it last 2 weeks, right? So if there's a flux change, there's an electromotive force. Okay, there's a voltage. Say if you put this magnet in a coil, and then flux is going to be stronger, right? then there's a current here. You know that, right? Okay? Okay? So this is Faraday's law. This is one of the fundamental laws of electromagnetic. And then you can pull out, then flux reduces. Also, there's a current here. Okay. Now, this is fine. Then, let's go to next. Then today, I want to talk about the transformer. Do you see that? Okay. So transformer is something like this. It's to change the voltage. Okay. If you have two coils here, right, connected like this, and then you change the current on the one circuit, then this magnetic flux is going to change, right? And the change of the magnetic flux is the same between these two, right? So that B divided by N is the number of coils, how many rotations there, is going to be the same because this is going to be the magnetic flux change. Okay? So this relation holds true. So if you change the number of coils here and here, okay, then you can change the voltage of your electricity, right? Okay, now I have a question. So this is primary and this is secondary, and then you have more turns in the secondary, right? So is the voltage getting larger or smaller? Okay, excellent. You guys are good. Okay, good. That's a step up, and then you can also make it in the opposite way, right? If you make the turns smaller here, larger here, then you can make the voltage smaller. Okay, and this is used in your daily life. So you know these electronic lines, these high voltage one, Taiwan also have it, right? Sometimes underground, sometimes on the high tower. They are very high voltage. Did you know that? Have you heard of that? They are kilovolts, right? So it's kind of very dangerous to touch around. So, you know, they usually have a fence, don't go in there. Why they are high voltage? Did you know that? Decrease the yes, Alice. Yes, exactly. Oh, you guys are good. So the energy loss is this. Depends on I square R, because you know these lines are basically resistance, right? And then if you put more current, they are bumped into resistance more. So the current is smaller, then the energy loss is going to be smaller. So how do you make this I smaller? Right. Then you make the I don't have that. You make the voltage higher with this. So the total power is B times I, right? So total power is the same. And B times I, maybe again, so B times I. Total power is B times I, right? Power is, right? So if you want to make I smaller, then you can make V larger, right? So if you make V larger, and the I is going to be small, so the loss here, okay, is going to be smaller. That's why these are extreme high voltage. Then you have a very little loss. But then this kind of high voltage, as we learned last week, is very dangerous for human. So in reality, at your home, we have 100 volt or 200 volt or something like that. We need to reduce. So this is why we have various transformers to reduce it to the, these small values, 100 volt in Taiwan, right? If it's 100 volt, even if you touch it, I don't recommend, but you probably won't die. So, but if it's a kilovolt, then if your current goes kilovolt, it goes to your body, you die, right? So that's why. Okay, it's about time to stop. So, yeah, this is some takeaway. This is why the high voltage lines are high voltage lines. Thank you again for the good presentation. I enjoyed them. So please make sure to submit your report. And then see you next time on Friday. Friday, I need to be at NTHU workshop, so I will teach remotely. So please, let's join online. Okay. But you guys set up, right? Here, right? So I think you guys can still come here and then meet our TS. Okay. Any questions, you can come to me. If you don't have questions, see you next time. Okay. Okay, thanks everyone.